Welcome to our webinar today. We are going to talk about the Raspberry Pi and how to use ITK natively in this board. So a first quick introduction about what is the importance of the Raspberry Pi. So a few years ago, a group of professors at Stanford started analyzing the number of people registering for the computer science degrees. And they found that there was a diminishing number of students entering the computer science programs and that they were getting with lower and lower experience on programming. And they tracked that to the hypothesis that these younger students were not having access to the type of computers that we used to have in the 80s. And where a lot of people learned to program with essentially home computers. And so what it did was to design something that was the equivalent of the computers that we used to have in the 80s. It should be cheap, it should be easy to use, it should be compact, and borderline between being a computer and being a toy. This is what we used to have in the 80s. This is the Commodore Vic 20. This machine used to have 20K of RAM, 20 kilobytes of RAM. So you really needed to think about every single command and line of code that you put in that machine. It was not considered a computer. It was sold in a computer in toy stores. And it was designed to be connected to a television set. So anybody with a television could be using this little device. So this is the Raspberry Pi today, and it's the size of a credit card. It's very compact, and the idea behind the design is that anybody, when they look at the card, they should understand what the different components are. They should have the view of the big blocks of the system. So what we have been doing recently is to experiment with the Raspberry Pi and see how far you can take it, what kind of things you can do with it. So we have been posting a series of blogs on it. We have been using node.js as JavaScript in the server side, compiled DTK on it, and did cross-compilation for ITK, and built also ITK natively on the board. And what we're going to do today is revisit this exercise of building ITK natively in the board. So let's take a quick look at what is it that you get in the board. So this little computer has 512 megabytes of RAM, and it has a system on a chip. Which means that you have the microcontroller or the processor integrated in a single chip with some of the auxiliary devices that control, for example, the input, output, and the pulse, and so on. So when you used to look at a typical motherboard in a computer, you will have the processor, and surrounding the processor, you have a family of chips that will take care of auxiliary tasks. The idea on the system on a chip is that all these auxiliary devices have been integrated into a single compact box. So you will see them a lot in mobile devices, cell phones, devices like the Kindle and the iPad. Now the processor that is using is from the ARM family, and it's also again one of the most popular processor families today. It's because of the abundance of mobile devices. There are more ARM processors out there than there are desktops. Now there are two models of the Raspberry Pi. The one that we are using today is the Model B, is the one that you will probably get today if you buy one. There was a Model A that is simplified and more compact, and they can still buy it today. It's a little bit cheaper. The Model B has two USB ports. It has one Ethernet port for the network. It has an output for high definition video. And it has an old type of TV signal that is still common for TV monitors. It's a composite output, so it's a single coaxial cable. And again, that was consistent with the idea that the device should be able to, anybody should be able to use the device with a standard computer. So most monitors, when you look behind the monitors, they will have a composite video input and so forth projectors. Then the power is received to a micro USB input, and it has very low power consumption. That is one of the key features of the Pi. So it's essentially 5 watts is what it will be consuming, so just 5 volts, 1 ampere. And that means that it doesn't need much heat dissipation. So it doesn't need a fan, it doesn't need one of these big bulky aluminum pieces of dissipating heat that you will normally see in any computer board. So let's take a quick look at the actual device. So we have here our camera. Okay, so this is, here you're seeing the picture of the Pi as it is in our table right now. So just to give you a quick closer look, The red plastic base is just for protection, so the actual card is just what you see in green. And to give you an idea of the size, so this is a hand-by comparison, so it's really the size of a credit card. And you have here the yellow connector is the video output, the black connector is the audio output. These pins here are for input, direct input, output, so you can use it for electronic projects essentially. Here we have SD card, so that's where the equivalent of a hard drive. So it doesn't really have a hard drive, you use an SD card, the same type of card that you will use for a camera, a digital camera. Over there we have the HDMI output, and here we have the two USB ports. Right now we are using one of the USB ports to hold a wireless connector that actually works out of the box directly with the Raspberry Pi. And the other one we're using it to connect it to this dumb laptop just as a keyboard. Normally you can use the Pi directly without having to connect these two cables, and that's actually how we're going to do some of the demonstrations today. We are essentially taking advantage of the fact that through the wireless connection we have the Pi on the network and we can SSH through the board. That's the device. If you're curious about what this is here, so this is the Atrix lapdog. It's a device that was designed to be used with a cell phone. It's a dumb machine, so it doesn't have a processor. It just has a battery, the keyboard, and the screen. But it has the advantage that it carries this HDMI connection. So it turns out to be an ideal device to be a complement of the Pi if you need to actually interact directly with the Pi instead of doing it through an Ethernet connection or logging in through SSH. Okay. So let's look at 2. Now you can run multiple operating systems, but what is very popular these days is to use a variation of Debian Linux on it, and it's known as Raspbian. So it's essentially the Debian Linux distribution that compiles all for the ARM architecture and a little bit customized for the size of the card. Typically, when you get these SD cards for this device, the typical size is about 4 gigabytes. So you have to compact the system a little bit to make it fit in there. You can find larger cards. I think you can get up to 64 gigabytes these days. They vary in price and speed. There's another distribution called Occidentalis, and this was prepared also based on the Linux Debian distribution and is created by this company called Adafruit Industries. So those are, it's a company that essentially does a lot of electronic devices for hobbyists. What we're using here in this case is a 4 gigabytes SD card, and originally comes with the Occidentalis system, so the Linux Debian variation. One of the advantages of using Occidentalis is that it is already configured to manage the wireless connection. So we just needed to connect the wireless USB dongle, and it was working out of the box. We just needed to enter through the console the name of the SSID of the network that we were going to connect to, and it was working right away. Now, one of the first things that you want to do, therefore, is to expand the system to use the full 4 gigabytes of the card. Just for convenience, when they send you the operating system, it is all compacted into 2.6 gigabytes. So it's not really using the entire size of the card, and you have very little memory to do anything. So during the configuration process of the Raspberry Pi, you want to expand it to 4 gigabytes. Or if you have a bigger card, of course, you want to expand it to the entire size of the card. All right, so once we're set up with your Raspberry Pi, one of the first things that you need to do is to compile or build CMake. So for doing that, we went directly from the basics. So you need to install the lib and courses library. The commands are used for installing as the standard Linux commands. So this is using apt-get. You want the lib and courses in order to enable CMake to build the CMake application that will show you essentially a small menu or a GUI, a text-based GUI for the configuration. We can use wget in order to get the files from the CMake website. Here the line is broad, but this should be also everything should be typed in a single line. So wget up to the .gc file should be a single line. And once you get this file, then you expand it with the standard Linux command. Again, use the tar file, the tar command, and expand it. And that should create a source directory for CMake. Then you go and create the binary directory where we're going to build it, enter into the directory, and run configure. So it's exactly the same process that you would have used in a Linux machine, or actually even in a Mac. Now what changes is the speed, because this is a low power device, it's a little slower, so it took 38 minutes to run through the configure process, something that typically in a modern laptop would be a few seconds. And then we go into that binary directory and type make, and that will take 70 minutes for the case of CMake. That again is a lot longer than it will take in a typical laptop. Today you can build CMake in about 2 minutes in a modern laptop. One of the things that's interesting to have in the Raspberry Pi, just to get more familiar with the speed and what you can expect from the device and what is too much to expect from the device, is convenient to install this application called IOTop. You may be familiar already with the top application that when you run it on a Linux system, will show you the list of processes that are running, how much memory they are consuming, how much CPU are consuming. So IOTop follows the same principle, but it will do that for the actual input and output that is coming out of these processes. So essentially it shows you how much bandwidth that particular process is using when reading and writing from the disk. So you install it with the standard command apt-get install, and then when you run it, you have to use the sudo command in order to trigger this, because it goes down to the kernel. Well, not to the kernel, but it needs access to some of the system files in order to track the usage of the bus. Now when we run this, as we were building ITK or CMake, this is what we get. We take that some of the processes, essentially GCC when it was compiling, was using about 30K per second up to 60K per second. So that's the rate, the bandwidth that is using on reading and writing. If you run the equivalent command in a laptop, you will get about 500K to 1.5 megabytes per second. So that's to give you an idea of what you can expect in general whenever you're doing transfers of files or copy pasting or building a system. This at least gives you the idea of how much to expect from the speed of the card. Doesn't quite relate to the speed of the processor yet. Okay, so why did we decided to build ITK on this device, and why we were confident that it could be possible is because when we look back at the history of ITK, in the year 2000 when we started designing ITK, the specification of the Raspberry Pi is exactly the type of desktop computer that we used to have 10 years ago or 12 years ago. So we were expecting to be able to build ITK in a 512 megabyte RAM machine, and about 100 or so megabytes of, megabytes of hard drive. And those were single processor for the large majority. So essentially, ITK was designed for a machine that used to be what the Raspberry Pi is today. So it should be possible to build it. We will not get the speeds that we are accustomed to today, but it should be functional on it. So the process we did was very similar to what we did for CMake. We just go directly from the Raspberry Pi. We type the wget command and type the path up to the most recent release of ITK. This is ITK 4.3.1. We expand the source code, and then we do the configuration with CMake. We create a binary directory. We're going to build ITK, enter into that directory, and type the CMake command, now that we have already CMake built on it. And we go to the configuration. Now, because we have a more restricted system here with the Raspberry Pi, we disable the examples, disable the testing, enable shared libraries, and enable the release option for compilation. And then we type make. We use the time command before make in order to keep track of how long it was going to take to build. And it's about 6 hours, 52 minutes, so probably 7 hours to do it. Okay, so let's take a quick look at the system. So what we have here is an SSH connection to the Pi. So when you get there, this is what you have in the top directory. The designers of the Raspberry Pi really intended young developers to get into, or young kids to get into programming. So one of the things they are putting forward is the use of Python and the use of educational tools like Scratch. Scratch is a system that was designed at MIT in order to teach programming to kids. It's very interactive. It follows the principles of Logo. So you have the ability of programming movements, moving north, south, west, east, and essentially scripting activities for things that look like characters in the string. So many of these tools are preloaded in the Raspberry Pi. You don't have to use them, but they are all there. And again, the idea is to entice kids to get engaged into doing programming. So what we did in our case is that we created an SRC directory in a home directory. We are using the default user. So this is the user called Pi. But you could create users as you do in any normal Linux system. And here is what we were building both ITK and CMake. So CMake is in the first directory, that's the source tree. And the second one, we have the source tree of ITK. And here in our bin directory, we have the build of the two systems. Okay, so let's just show a little bit how the configuration looked like for ITK. So I call the binary of CMake that we built directly in the Pi, giving this directory, and this is essentially how the configuration was set up. So disable examples, enable shared libraries, disable the testing, enable release, and we have all modules to build. Okay. So now that we have ITK built in there, we can start using examples. So we can do something like creating a directory for the median filter. And we copy an example from the ITK examples directory, so we can go for something like source inside examples, filtering, and the median image filter example that we have there. We can put it in here. And we can copy from the installation examples, we can copy the basic CMake list file and we can modify it. You have to install Vim as well. Vim was not directly in the system, and this reflects again. In order to get to that small space of 2.6 gigabytes, the default installation of Raspbian and Occidentalis do not have many of the things that you will have by default in a Linux system. So it doesn't have Apache installed. It doesn't have many of the editors. And the idea is that you install as you need. So you actually just load the card with what you're actually trying to use. And part of the expectations with the Raspberry Pi is that you will use it for doing kind of embedded projects. So maybe program the card to manage a camera and do a home project. Use it for driving devices, driving robots. So it's really expected that you're not supposed to install a full desktop system on it. Now you can, of course, do some of those things, but more of the expectation is that it's a device for hobbyists and for education. So let's open this CMake list file. We're going to do a couple of edits in order to adapt it to running our media filter. Okay, so we have the typical lines. In the first line, we select the version of CMake. We can actually pump up that to V2.8. And then we have the name of the project. We find the package ITK as usual, to the include of the ITK use file, and declare the executable file and the target libraries that we're going to link with. So as usual, we do the ITK libraries under ITK underscore library symbol. So we have our two files here. We can create now a bin directory. We go inside that bin directory, and from here we call CMake and refer to the directory where we have the sources. We hit the C key to configure. So as you can see, all the process is pretty much identical to what you will do in a standard Mac or in a Linux machine. So any Linux or Unix-based system will look very similar. So here's reminding us that we have not told CMake where ITK is built, so we are going to do that. We say that we want to do a release build. And we point out to our location of ITK. Configured, and after configuring, we generate. And here's where you can see the difference. When we do make, it's going to be slower than you may be accustomed to see in most standard computers. Now, one of the tools that we are using here, and it's actually very useful, is called tmux. Tmux is something that you really always want to install in a machine. It's similar to Scream, if you are familiar with the kind of tools that once you SSH to a machine will allow you to manage multiple screens. So both tmux and screens are extremely useful. I've been using tmux recently, and it's very easy to use. It allows you to split screens. And if you disconnect from the machine, it will keep your connection open, which is very useful if, for example, you're building ITK and you need to disconnect from the device. If you kill the connection, the tmux application keeps the login in the remote machine active. So processes that you were running there keep working, and when you connect back, you can see them again. So the Raspberry Pi is a single core machine, which is interesting because today you find phones that have quad-core processors. Actually, what we can do is to show top on the other screen. So, actually, let's show top. So this is where you can see the rate of reading and writing on disk. So on the right side, you have the list of processes, and then you have the rates on bytes per second as it's writing. See if it is nice linking. So we should see LD at some point appearing here. One of the interesting features of the Pi is that because it has such a low power consumption, you can actually feed it with small batteries and make very portable computers, or very portable devices that you could put, carry along, or put in a wall, or put in a place where you don't always have power connections. Okay, so this finished building. It took 2 minutes to compile the medium filter. Okay. We have there our executable. And now we're going to need a couple of images, so as usual, we can copy those images from the examples in ITK. So we can go back again to the source tree, go to the examples directory and data, and let's take our common example of the brain proton density slice image. Here. And then we can run the medium filter on it. Okay, so we have our output. Now, because I'm connected through an SSH connection here, I cannot display the image. So one thing that we can do is to go back to the laptop and try using the camera. So the screen is very reflective, so you may not see exactly what it was. Let me find the directory first. Okay, so you can see it has a desktop connection that's very similar to what you have in a Linux machine. And we have here our output image that we just generated. Oh, it's the window. Okay. Yeah, there is more reflection on the screen. Okay, here it is. So this is the desktop application. I'd say these are some of the applications that I was talking about at the beginning. So we have the typical file navigator, file system navigator. You have your terminal, and you have plus Python installed on it. The web browser is called Midori, and you have here your setup for the wireless connection at the bottom. This is very tricky. So, you know, there's a similar situation as if you were logging into a Linux machine. So, I'm logging into a Windows machine, so otherwise I could have used the remote X system connection to show you the image. Okay. So let's do now one of the registration examples. So similar exercise, let me clear the screen. We can copy the source code from the inside toolkit 3. We go to examples, registration, and we can grab, for example, the email registration 5. And now we have the CMake file. We can copy it from our previous example of the media filter. We modify that file. Now we can create a binary directory, go into the binary directory, and use CMake to configure. So again, it will tell us that it doesn't know where ITK is, and we will provide the path to the ITK build, select the build type, and then proceed with the configuration. Again, we can do the builds. So let's go back to the other screen in TMOS, and we monitor with IOTop. We can do a little bit of top to see the processes as you're working through it. So you have the C++ taking 95% of the CPU. Something strange about the refresh here. Okay, and let's take a look at IOTop. Crunching. So as you use it for doing some of the typical image analysis that we do with ITK, so think, for example, of a typical MRI image will be in the range of 100 megabytes in size. So you have to keep remembering that the RAM in this device is 512. So if you load one image and filter it and get an output, then you pretty much are saturating the machine at that level. So you probably don't want to have more than 1 or 2 copies of a data set in memory at the same time. On the bright side, even in this machine, then you could take advantage of the streaming capability of ITK. So even if you have a larger image, you could still process it if you pick some of the filters that have streaming capabilities. So in that case, what will happen is that ITK will cut the image into smaller chunks, and it will process the sub-pieces through the pipeline and compose them at the output. Now, this is a 16 bits processor, so something also to keep in mind when you're dealing with integers and different types. One of the interesting reasons for building ITK and some of the other tools in the Pi is that because you're building it for an ARM processor, we are kind of verifying that we can run in ARM machines. And when you look at the abundance of devices that use ARM processors, you have pretty much all the devices that are running Android today as mobile devices. If you look at some of the Chromebook devices that Google is putting out, there's a Samsung one that is in the order of $250, and that's an ARM processor as well. Devices like the Kindle also have ARM processors, and in some of those devices you could install Linux and run directly this kind of application, so do the same process of building directly in the device. Okay, well, this is building. Let me show you some of the other things that you can do with the Pi. So, because it's designed to do projects with electronics, you can also use the connections of the GIO port to get connections directly to a breadboard. And in that way, you could work on electronic projects. So, essentially, do things like driving LEDs or microchips and driving those from the board. So, the set of instructions that you find in the Pi will allow you to essentially enable or disable those pins directly and read data in and out. And there is a large collection of projects. If you just Google for projects in the Raspberry Pi, there are hundreds and hundreds of projects to be done with it. Some of them are really interesting and pretty clever. So there is one that is a very minimalistic project where they did an FM radio with the Pi by just connecting like about 10 centimeters, 20 centimeters cable to one of the I/O pins. So just by wiring that and turning it on and off, the speed of the processor is enough to actually have an RF signal. So without any further electronics, you could have a radio signal that is being transmitted for a single cable. And that's an illustration of how this device helps people to go back to basic principles, to understand again how computers work, how electronics work. Because one of the challenges is that we have become too disconnected from the machine. We are separated by the GUIs and the IDs, and we tend to forget that there is a set of chips down there that is actually working and taking all the computational tasks and that we are requesting. Okay, so the registration is still compiling. So you may be able to see, depending on the refresh on your side, you may be able to see some of the burst of activity in the disk. So for example, there is one there of 13 kilobits per second. When you're using tmux, you can use pretty much all the commands for tmux are using the Control-B key combination. and then a second letter. So you could create a new screen by using Ctrl-V and C for create. And once you want to look through the screens, you can use Ctrl-V and next to go around. At the bottom of the screen is going to show you how many actual screens you have open, and it kind of reminds you what processes are running in there. So in one we're running make, in the other one we're running sudo for sudo iotop, and in the third one we're running just bash. So it's a very practical way to deal with a single SSH connection, have multiple screens open. One of the things that it doesn't do is that it will not accumulate the buffer, the text buffer. So if you have a process that is printing a lot of data to the screen, Tmux will not let you scroll up and recover previous commands. That's one of the few things that you will notice as a difference when you're using it in a remote connection. Okay, we got to linking. Let's see how that changes our iotop output. So we have some bursts there, 15 kilobytes per second. Okay, and it's built. So it took 7 minutes. So let's try running it. Again, we need some images, so let's copy some images from the examples. Examples data, and we can grab the brain proton density slice that has a border of 20. And we have that same image rotated by a certain amount, 10 degrees. We have our two images here, and we can run the registration process on it. And that will be the registered image. And let's put time at the beginning so we can see how long it takes. So as usual, it's going to print the value of the metric, so, and it's diminishing as the optimizer is working through the parametric space, and it's printing the parameters of the transform. So this is using a simple rigid 2D transform. So we have the translation on the right side, the two last numbers, and this is computing the center of rotation. That is not really necessary, but and the first number is the actual angle in radians. Now when this is running here, we want to look at the top output. The display is not looking right here. Something is getting confused between the use of Tmux, so it's not refreshing correctly the way the screen should look like when you're using top. Let's go back. Okay, and we have the 1 minute of execution, and we have the typical output there. Okay. So that's our basic tour of how you will use ITK in the Pi. So essentially the same process that you will go in a Linux machine. You have to build CMake to have a very recent version of CMake. You can actually install CMake in the Raspbian system, but it's not the most recent version. So something that tends to happen with Debian is if you are using the stable version, you will have not necessarily the most recent versions of the packages. Okay, so let's take a quick look at an interesting application that is nice to use along with the Pi. And this is because in the typical situations when you will use a Raspberry Pi, you will be connected to it remotely. And because of the characteristics of the device, it makes it a very nice web server or file server remotely. Now you can do it simply by installing Apache on it. But one of the new tools that is very interesting to use with the Raspberry Pi is node.js. So let's take a quick look at it. So node.js is essentially JavaScript. If you're familiar with JavaScript, you probably have seen it working on the website, on the web server side, so in the client side of an internet connection. Most of the browsers will have JavaScript engines. So when you open a web page, you will have HTML text in that page and potentially some scripts written in JavaScript. Those scripts will be executed in the browser as kind of a contained environment. The idea with Node.js is that they took the language of JavaScript and they put it on the server side so you can run JavaScript code the same way that you will execute Python code or C++ code. So you have an interpreter that will go through this code. So it's actually closer to Python than it is to C. Now it's using the same Google V8 engine that is using the Chrome web browser. So it's a very high performance engine for doing JavaScript. And one of the interesting features that it has is that it performs asynchronous calls, meaning that it essentially has a very rapid event loop. And every time that it calls a function to execute, it doesn't wait for that function to finish before it goes to the next instruction. It just essentially spawns as a separate task without having to use multi-threading. So it has a nice integration with the operating system in such a way that it is starting to invoke calls, and those calls go and execute by themselves while the loop continues working. So because of that configuration, it gives you a very rapid response. So it's always listening to incoming events. So typical usages, you can use it as a web server, as a file server, event manager, or the database driver. Now, if you think about how to combine it with ITK, one natural combination is that, as you noticed when I was running the examples, I have an image that I cannot look at it directly through the SSH connection because I'm in a Windows machine. I could have something like the Atrix lapdog and be connected directly to the Raspberry Pi. I have a keyboard, I have an HDMI monitor. But then another option is to use Node.js and set up a simple file server, a web server, in such a way that I could run an ITK process on it, or actually any process, and have some of the output files to be visualized through a web connection. So that's what we're going to do in our last section here. So how do you do that with Node.js? Of course, you have to start by installing it. The installation process is identical to what you would do in a Linux machine. So I call apt-get, and Node.js is the name of the application. And you also need NPM. NPM is the package manager for Node.js, the same way that you have other package managers for Python and other applications, things like Ruby, for example. So there's a collection of packages, and NPM will drive those particular packages. Once you have installed NPM, you want to update it so it knows what packages are available. And then we want to install these two helper packages. One is called util, and the other one is called connect. And the functionalities that these two packages provide is with a few set of lines of code, we can set up a file server in the system. So let's illustrate that. So this is the example with Node.js, and we have just an HTTP server. So this shows you how simple it is to create an HTTP server with Node.js. These few lines of code at the beginning, so this is JavaScript. This is essentially the command that is creating a web server. These two lines here are just grabbing the current time in the system and displaying in the console, so it's mostly informative, so we could actually remove those lines. And these 4 lines here are writing the header of an HTTP page, writing 2 messages, and then closing that connection. And the last line is selecting the port in which we're going to run this particular web server. So this is going to do the equivalent of, in a very simplified way, it's going to do the equivalent of what Apache is doing typically in a system. So we run this here, and now we can go to our browser. And here we have the IP number of the Pi, and we select that port number. Let's see if I get the right number. 124. 83. Oh, I made a mistake in the IP number. It's 34 here. Sorry about that. Okay, that's much better. So we have the two lines that are coming from the node.js server. If you look at the actual source code of the page, it's really those two lines. So this is, again, going back to a minimalistic use of devices that hopefully is going to motivate or make it easier for people to get back and to get familiar with the essential aspects of computers and go back to understand how things work below the level of complexity that we are actually used to see them these days. So if you look at any web page and try to look at the source code of that web page, you will see that there are multiple pages of code and not always necessarily useful. In these cases, we are going back to look at those particular things that actually make things work. Okay, and we're getting close to the end here, so let's show the example of a file server. And in this case, what I'm going to do here, so this is the file server, and what I'm going to do is to copy here the two files that we got from running our examples with ITK. So we're going to copy here the source examples, the one that we with the medium filter, the directory, the output PNG, we copy it here. And we're going to copy the one that we get from the registration example. In registration. Okay, so the files that we have here now are these, the file server that we're going to look in a minute, a very simple index HTML, and we have the output of our image processing. Let's take a quick look at the file server. So it's these 6 lines of code. So the first 2 lines are opening packages, so the util package and the connect package that we selected. We pick a particular port. So as opposed to what Apache does, Apache normally would be running in the port 80. Now you could run in other ports, but in this case we are selecting this particular port. We could have picked any other number. And then this line here is the one that actually does most of the magic. And this is actually creating a file server directly there. This dir name refers to the current directory where I'm going to run this command. So what it does is that it's going to take the directory where we are in and it's going to expose that to external connections. So with a web browser you will be able to navigate the current directory. And the last 2 lines are just printing a message so we know what port we are running. Okay, and remember we're going to be running in the port 8888. So we just run node.js file server. It's now listening in that port, and we can go back to the web browser and connect to that port. Right, so, and I didn't show you what the content of the, so what we're seeing now is the HTML page. Yeah, it's the same as if I have actually put directly here the index HTML page. Okay. Now, because we know that in that particular directory we have the other files, we can put those names here and see the output from the web browser. So this, we are seeing this in my web browser in my laptop that is connected to the Raspberry Pi, taking advantage of that file server. And now we can change the image with a register. So this is the output of the registration. So again, it's a very primitive way to do it, but that's kind of the point with the Raspberry Pi. You want to go back to the basics of how things work. It's not very fancy. We can do it a lot fancier. We could have created a nice web page that will allow you to select some parameters and so on. And it's actually probably a good project to do if you wanted to use the Pi as an image processing machine. Okay. And this concludes the topics that we wanted to cover today. So I guess we have some time for questions, maybe?